Alright, we're going to look through the PowerPoints, plus I'm going to give you some additional information about how gel electrophoresis works today, some of the chemistry behind it. I think that'll make more sense, let you understand why we put together and use the apparatus for gel electrophoresis as it is. I think you need to know some of the background. That'll make it clearer. So I'll do the PowerPoints probably here at the end, but first, before we kind of do that, I want to go through and kind of draw some things for you and get some terminology down. So let's see here. Let's see if this works. I'm working on a different computer this week. The microphone just completely went out this week. It was bad, and if you've listened to some of my videos, you know how bad it is. And so let's see if this one is any better. So what we need to talk about first is gel electrophoresis uses, it's called a gel. All right, and a gel, think of it as like jello, and so we're going to have this like a slab of jello, and like you'd put it in a dish and you'd pour it in as a liquid and it solidifies over time. So you kind of have this slab of jello. If you look at it that way, if you think of it on the side, it would look like kind of like this. You know, looking at it from the side, but looking from above, it would look kind of like this. And now we don't make it out of jello, of course. The actual compound is agarose. All right, and agarose gel has some interesting properties. It's porous, and it'll let things pass through it, and it will small things pass very quickly through it. Large things pass slower, and that's going to be very useful for gel electrophoresis. What we're going to do is we're going to pass DNA through it. So how do we do it? Well, when we make this, let's go undo here. When we make this gel, we're going to form it in such a way with a little mold called a comb. And it's going to leave little like wells, is what we call them, in here when we form it. And it's kind of like if you were to take a spoon and dip out a piece like that. You take a spoon and cut out a piece, and so those are called little wells. All right, and the idea is we're going to put our DNA in there. All right, DNA is going to go in your wells. So that's going to have DNA. Now it's going to be in a liquid form. We will have chemically digested it, and we would have put our DNA into the well using a pipetter, which we will see in the PowerPoints. Now, where do you get your DNA? Well, you take your organism, say your fly, and you chop up your fly, literally, and you extract the DNA from the fly cells, the cells in the fly. So the idea is to extract your DNA, but this is going to be raw DNA. We're going to add another step called digestion. All right, and we're going to use something called a restriction enzyme. So let me write that out. Restriction enzymes. And these restriction enzymes chop up the DNA. So we have a piece of DNA, and there are certain sequences on here that are going to attract, so two A's, they're going to attract a restriction enzyme. It's a protein, and that protein will stick at a particular sequence, kind of like RNA polymerase sticks at a TATA box. These restriction enzymes are going to have certain sequences that they're going to attach to, and when they do, they're going to cut the DNA. So it's going to cut the DNA so that we have two fragments. All right, a short one and a long one in this particular case, but it could be more. All along here you might get this sequence, and it might cut it in several places. Those are the things that let us distinguish one piece of DNA from another, or how many fragments and what size those fragments are. That lets us distinguish one piece of well, longer DNA from another by seeing how many fragments it breaks up into and what size they are. So the idea here is we're going to chop up our DNA and we're going to put it in here. Now, what that means is we're going to pull that DNA. So it's all cut up now. It's in fragments. We put it in here. And the thing is, the small ones move through here very quickly. And so the small ones are going to end up down here in a certain amount of time. But the large ones take longer to move through the gel. And they're going to end up here. So this is telling us that this is a larger piece than this. Now, how large? Well, we usually have something called a ladder, which are pre-made pieces of DNA. And they might be like, here's a short piece, and then a little longer, and then a little longer, and then a really long one maybe. All right. Here, all right. So you have several pieces here, and they're different sizes, and we know that ahead of time because they're made artificially. So maybe this one is 50 bases, this is 100, 150, and 200. So if we put a ladder in here and we saw this, we knew what sizes these were. Well, we know the short one, that's 50, that's down here, and then 100, and then 150, and then 200. So we know that this one is between 150 and 200, maybe a little closer to 150. We know this one is really close to about 50. So we know our sizes. We know this one would be 50, and this one would be like 150, and our whole size is probably 200. All right, so that's kind of what we're doing. Now let's do something a little different here. I'm going to, let's make a new page so I can draw some different things. And let's talk about the chemistry. So we have our fragments. We're going to put it on our gel, and we're going to put it in a dish, all right, a container of some sort, and we're going to put our gel in there. And here's our DNA. All right. And we're going to cover this in, let's make it a little taller here, in a liquid called an electrolyte. And the electrolyte, which I'll talk specifically about in the video with PowerPoints. If I don't do it in this one, I'll do it in a separate one. This electrolyte, all right, here is essentially a liquid that can conduct electricity. And what we're going to do is we're going to hook up to the power, like a battery, or plug it into the wall. It's called a power supply. And we're going to hook up the negative up here on the side of the DNA, and then we're going to hook up the positive down here. There's a reason for that. DNA has a negative charge. All right, and so if you remember, things that are the same repel, but if they're different, they're going to attract. And so by hooking this up to electricity and knowing that DNA has a negative charge here, it means that the DNA will be drawn in this direction by the positive charge, but it will also be repelled by this charge, so which is negative over here. So by hooking up electricity to this and putting the negative here and the positive here, then putting the DNA in between them, you're kind of pushing from one end and pulling from the other, and the DNA is going to be pulled in this direction. And as it goes through this gel, it's going to run into barriers. And these barriers, this is porous, it's like a sponge. And there are big holes and little holes and things like that in there. And what it means is the little pieces, if we think of it this way, they're kind of like barriers. They're things that impede the DNA as it goes through here. And a big piece of DNA is going to have a hard time getting through all of this to get out. All right, if you want to think of it that way. But a little piece of DNA can just zip right through really quick. So little pieces move through here quickly. So think of it that way. Small pieces are fast. All right, large pieces are slow. So after a given amount of time, you get the little pieces down here and you get the large pieces stuck up here. And what that's going to look like on our gel, all right, let's change this around some. Let's get another new one. All right, what that's going to mean is that over time, you're going to, let me just do it over here. You're going to have, your DNA is going to move through this after you hook up the electricity to it. And the large pieces are going to be stuck up here, and the smaller pieces are down here. Now you're going to have also a ladder, like I talked about. You're going to have a piece where you know the sizes already, and they're going to be lined up over here, and that's going to tell you exact size. Now if you let this run too long, everything just runs out the bottom. But by slowing down and the small pieces, hold on. The small pieces will not be slowed down. They'll just zip right through, and in the same amount of time, while this is down here, the larger pieces will be much slower migrating, and so they'll be stuck up here. And so that's the idea. The latter are pre-made pieces, which will give you an idea of the size of your fragments. So like I said, you take a regular piece of DNA, you cut it with your restriction enzyme, you end up with what? 2 different sized pieces. You run it through here, you identify the size of the pieces. Now the thing is, you can compare organisms. All right, whether it's 2 humans, and you want to see if they're related or something. If they're related, they'll have similar patterns. If they're not, they'll have different patterns. 2 organisms or a mutant. Maybe you have a mutant and it gives you this size, whereas the wild type gives you something like this. Now another thing to keep in mind is if 2 pieces are about the same size, so you cut something and it's about the middle and these 2 are the same, then you're going to get a fragment here that's thicker. And that's telling you, oh, I have more than 1 piece that's about the same size. So that's also something you need to recognize when you're looking at a gel, is that the thickness also makes a difference. All right, I think I'm going to stop here, and I'm going to make a completely different video for the PowerPoints.